So the final video for chapter 7.8 deals with the second type of improper integral, which is when we have an unbounded integrand. So somewhere on the interval of integration, the integrand becomes infinite in the vertical direction. So it typically happens at an endpoint, but it doesn't need to happen at an endpoint. The infinite discontinuity can happen at either the endpoints or an interior point. So somewhere on the interval of integration, the integrand becomes infinite. And what that implies is that we have an infinite discontinuity. So in the vertical direction, we have a problem. Okay. So it's a similar process. We're going to replace the point of discontinuity with some C. So we're going to replace the point of discontinuity with C, and then we're going to evaluate it using limits to see if it converges or diverges. So then we'll evaluate the integral using one-sided limits. To see if it converges or diverges. So we're going to look at the different cases. Converges or diverges. Alright, I'm going to pause here and bring in my charts. So here we examine an example of this integral, and we see that at the lower limit of integration we've got a discontinuity, and at x equals 0 this is undefined, right? So we've got a problem here. So we can replace 0 with c. So we're going to rewrite this integral, and it's going to go from c to 1 over x dx. And we're going to go about integrating it, and then we'll use the limits to see as c approaches 0 from the right hand side whether this is going to converge or diverge. So one last point here, and I did make it on the prior slide. The function can be unbounded at either the endpoint or an interior point. So let's look at a case. This is a left infinite discontinuity. So this is the first case. Let's go on here. Case number 1. Suppose f is continuous. On the interval a, open at A and closed at B. So we're going to look at the limit. So I'm going to rewrite the integral from A to B of f of x dx, and I'm going to rewrite it as a limit. I'm going to come back over here. So this is going to become the limit as c approaches A from the right, because here's your, grab another ink, here's your interval of integration, and we're approaching A from the right hand side. You're moving right to left, so we're going to look at a right sided limit in order to look at the left infinite discontinuity. Okay, so we're going to rewrite this as the limit as c approaches A from the right hand side, and then I'm going to replace the discontinuous point, which is A, with c, and then evaluate the limit of the integral. We'll take the antiderivative, and then we'll take the limit of the result. And again, provided the limit exists. And if it exists, then it converges. The second case is when you've got a right infinite discontinuity. So at the upper limit of integration, you've got a problem. But everywhere else, f is continuous. So case 2, we're looking at f is continuous everywhere, but at the upper limit of integration. So it's continuous on including a and open on b. So we're going to rewrite the integral from a to b of f of x dx as a limit. So this is going to be the limit. And here, grab another ink, right here's our interval of integration, and we're approaching b now from the left-hand side. We're moving left to right. So this is a left-sided limit that we're looking at. So c is going to approach b from the left-hand side, and we're going to replace the point of discontinuity with c. And provided the limit exists, if it does, then this converges. So this is our second case. And we'll primarily, for simplicity, the problems get quite long if we have infinite discontinuity and at an interior point. But just like we had, a negative infinity to infinity, so you have a completely open infinite interval of integration, the same sort of thing can apply here. You're going to have to break it up into pieces. So that's case 3. So case number 3, it happens at an interior point. So this is at an interior point. Suppose f is continuous on the closed interval a and b to b, except at an interior point. I'll call it p. So this is interesting because this case shows that if a function is unbounded at c, it may be possible to integrate that function over the interval that contains c. So that's an interesting point here to make. Okay, so here we've got the integral a to b f of x dx. We're looking at a point of discontinuity at p, so we're going to break this into 2 limits. We're going to look at the limit as c approaches p from the left-hand side. Okay, so now we're looking at this piece. Make sure you can see that's the c. So this is c. And we're going to add to it the limit as d approaches p from the right-hand side. So now we're looking at this guy. And that's going to be the integral from d to b. And then we're going to examine the limit. And provided that both of the improper integrals on the right and the left exist, then this is said to converge. If it doesn't, if one of them doesn't, or both of them do not, then this is said to diverge. So, if the limit exists, the improper integral, like both limits exist, then it's said to converge. If it does not, then it's said to diverge. So at this point, I think it's time for an example. Okay, here's the example that I'd like to go through with you. It's textbook number 29, and we're asked to evaluate the integral or state whether it diverges. So you can see here that at 1 we have a problem. We've got an infinite discontinuity. So on the interval 0 is good, but 1 is open. We've got an infinite discontinuity at x equals 1. So, excuse me, I'm going to rewrite this limit. This is going to be the limit, and we need to look at approaching this from left to right. So this is a left-sided limit, and we're going to replace 1 with a, and we've got to find the antiderivative here. Don't lose sight of your basic integration tools. Right, so I'm going to do a u substitution here, and hopefully you see that right away. We're going to let u equal x to the 4th minus 1, and du is equal to 4x cubed dx. And dx is equal to du over 4x cubed. Just a little refresher for you. So this is simply 1/4 the integral from 0 to a 1 over u du. And then I'll put the limit back in. And I'm just going to hold on to this piece of it for now. So take the antiderivative, and I get 1/4 ln of u. And I'm going to back substitute. This is 1/4 ln of x to the 4th minus 1. And then evaluate that between 0 and a. So I'm going to put the limit back in. This is the limit. Actually, I'm going to pull out that 1/4. Let me just write it. So this is the limit as x approaches a from the left of 1/4 I think my capacity of all these videos is nearing its end. X to the 4th minus 1, and evaluate that between 0 and a. I'm going to pull out the 1/4 on the other side of the limit. So it's 1/4, and I'm going to use the fundamental theorem of calculus here. A to the 4th minus 1 minus 1/4 ln of 0 minus 1. And again, that's why we have absolute value signs, because look what happened here. We went negative, and you know that ln cannot, the logarithmic function cannot take a negative argument. So the ln of 1 is 0. So this term is going to 0. So this boils down to 1/4 the limit as a approaches 1 from the left of ln of a to the 4th minus 1. So what's going to happen here? And I would ask you to think about the log graph. Okay? And think about what happens. So as we approach 1 from the left, as we approach 1 from the left-hand side, this limit, as a approaches 1 from the left-hand side, this term, right, is going to get extremely close to 0, and that limit is going to go to negative infinity. So this diverges. And that's it.